Okay, good. There's no strict timeline. So,
Okay, the
Yeah.
end time is 1 hour.
yeah, it's great.
Okay, let's get started, and thank you all for coming today. So we're very happy to have Dr. Kai Zhang from WPI, and Dr. Zhang is a associate professor in biomedical engineering and robotic engineering with appointment in computer science, and he is founding director of Medic Frontier Ultrasound Imaging and Robotic Instrumentation. And his research interests including advanced medical imaging robotic system and with emphasis on ultrasound and photoacoustics. Dr. Zhang received bachelor degree and master degree in human health science from Kyoto University, Japan. And then he got master degree and PhD in computer science from Johns Hopkins. And Dr. Zhang he got this NIH Director Award, DP5, back in 2019. And he's also the Early Investigator Award for DoD Prostate Cancer Research Program. He has served as a program committee member for multiple tracks in SPI medical imaging, including ultrasound imaging and tomography. Many of his research, actually, we have so many common research interests, including he's doing photoacoustic imaging for guide the atrial fibrillation treatment, mostly on RF ablation. We're doing something similar. And also, we both work on robotic ultrasound with different applications. It's our honor to have Dr. Zhang here, and please join me and welcome Dr. Zhang.
Thank you. Thank you, Dr. Sean, for kind introduction, and very glad to be here, flying from Boston to Irvine. Had a chance to talk with you in person today. Yeah, I mean, I see there are a lot of common interests with our lab and Dr. Sean's lab, but also enjoying learning a lot of research ongoing here at Beckman Institute, especially expert in optics. And hopefully I can kind of introducing another paradigm that I know that probably a lot of speakers talking about imaging and optics, and we are working on imaging, but we're also working on robotics. So probably hopefully can merge those flavors together throughout my talk. Let me start from where I'm coming from, right? So some of you heard, some of you may not heard, I'm coming from WPI, Worcester Polytechnic Institute, and we are third oldest STEM-focused institution in the United States. The oldest is RPI, the second is MIT, then WPI. And from its name, we are very focusing on engineering STEM degree, and robotics is one of our flagship program, and we have first robotics program degree from undergrad to PhD, and we recently now made a department as robotics. So I'm part of robotics. So I have a lot of students doing pure robotics and interested in medical robotics. And I'm also, more focused on biomedical in my research. So blending those flavors together. And another thing that I want to emphasize here is we are very eager to adopting those technology for translational medicine, translation in a clinical scenario, where we recently launched a facility, so-called practice point, where we do have those mock patient suites, and this is C-arm CT. Then at the back of going toward the screen, there will be a 3 Tesla MRI machine from GE, and we have surgical room, and many of them. We don't have a hospital, so many of them are actually intended for research. And the idea of this practice point is we are merging the force together from academic side as well as local industries such as Boston Scientific, car stores, Medtronics, and those companies, and try to building the ecosystem around the New England or Boston or Massachusetts area. Then under that environment, what we do. So my lab is particularly interested in integrating imaging and medical robotics. So there are people working on imaging, exploring new visualization capability for cancer or brain imaging. There are also people who are working on medical robotics, building those Da Vinci surgical robot or robotic for interventional procedure. And I would say like our strengths as a lab is we do both so that we can think about how imaging can be helpful for robotic procedure. For example, we're not only doing just imaging in photoacoustic and ultrasound, but we're thinking how those imaging can be adapted into surgical robotic system. I want to show some example here. Then the other side is how we can leveraging robotic technology for imaging for good use. For example, imaging traditionally, let's say optical technology or ultrasound technology, majority of them are still very manual. I would say like ultrasound is very manual in a hospital. So we are very interested to think about how robotics, as we now AI is so developed, how we can leverage their strengths and make the life easier and even do something that human alone cannot do. So that's something I hope I can talking about today. So let's start from the first one, okay? The way I introducing or as a general, like why we were doing imaging is I usually want to start from this picture. How many of you have seen the like medical robotics system like Da Vinci before? Good. So the question I want to ask is, where is the vision of this robot, right? So where the surgeon can get information about where to treat or where to cut and so on. Does anyone have any thoughts? We don't have any camera like randomly surrounding, right? So the only camera actually in this robot is here. So there's a laparoscopic console here, and there's other arm. So in a laparoscopic procedure, so there are many arms try to do surgery, right? But the only vision is at here. And this is how it look like. So we can see the tool, we can see the suture scene, and there are a lot of medical robotic research and how to make those technology more useful. But at the bottom line, those are limitations in terms of the information they can have access to. But we all know that that's not only the information that doctor want to use. For example, if they want to even expose this scene, there will be a layer of fat or those tissue they need to kind of like open up first, right? Or once they open up, they want to know where the tumor is located inside of the scene. So a lot of information are hitting from the surface. That's where they don't have access to. So our interest is how we can advancing those imaging technology from those vision technology that currently they have access to, but telling where and where to treat and where not to treat, as well as when they should stop the treatment. Then speaking about like how they can basically go get those information, because if they want to do procedure effectively and correctly, they need to have a medical imaging technology that can see through, right? So this is one of the example as a solution where there's a surgical room, has a MRI, there's a patient bed and so on. So this will probably answer the question that previous slide cannot have. And this is a picture of Amigo system at Harvard Medical School. Okay, so if you have $1 million or a lot of money funding as a big hospital, have this capability, that's fantastic, right? But we cannot reproduce this Amigo platform everywhere in the world, everywhere in the States. So, so this is, for example, the example of the prostate procedure guided with PET guidance as well as MRI image and CT and so on. But the idea here is what we want to introduce our lab is how we can make those image guided procedure more accessible. in a lower cost and in real time. And that's where really ultrasound and photoacoustic has its strengths. So I have a slide to introduce photoacoustic, but I think the majority of you may already heard about this technology, but just what goes through very free. Basically, the idea is we are sending the light, right? Then the light will be absorbed by the tissue, and we're creating thermoelastic expansion, and that acoustic wave can be received by ultrasound sensor for detection. And why we want to do this process is because we want to take advantage that different wavelengths of light will absorb by the tissue differently, and we can use this to, for example, get the tissue oxygenation, or we can do more localized cancer imaging if we have molecular target that can absorb at that particular wavelength of the light, right? And there are a variety of applications using photoacoustic, some for vascular imaging, some for tissue characterization, differentiating, blood and collagen and so on. And there's also molecular targeted application using photoacoustic, and some are more for interventional cases. So these are indeed the technology that we're exploring significantly, and we want to replace in this room, hopefully, with a very like a benchtop system equipping with ultrasound and so on, and photoacoustics. So what I want to go through today, first half, is how we can make it happen. Like I wanted to showcase you that indeed we can have photoacoustic to tell where the procedure should treat and where they should not treat, and also when to stop the procedure. So these are common questions that surgeons want to have when they approaching to the patient, and we're trying to pitch in a way that we do have such a complete package that they can appreciate. Okay, so let's focus on these three things. The first thing I want to start off with where to not treat, because that's the first thing doctor will do when they start cutting the patient out. For example, I mentioned at the beginning about the laparoscopic procedure using Da Vinci system, right? So the first thing they will approach to the organ is not to see the cancer, but to reach the organ first. And in order to reach the organ, they always have to first making sure that there are a lot of like a fat tissue or irregular, tissue layer they need to cut through, then ultimately see the organ. Then the challenge for those procedures is when they are cleaning up the environment, there's always those critical structure they don't want to damage. In case of prostate, this is an example of prostatectomy to remove the prostate. When they are cutting through the area, they are like a nerve bundle, there's a vascular bundle. Once they're cutting or touching, will causing severe complications. So they have to be very careful to ensuring that they are doing things in the right way. So you can think about, but currently it's done in a blind manner, right? So if you want to walk to certain distance, then if you don't have any light, it's going to be very challenging. You have to be very, very careful to go step by step. That's how what is happening. They want to go through like a centimeter of the layer by taking like half an hour time to not damaging those structures. But if you have a light, if you have the information that what is in front of you, then you can do more effectively approaching this problem. So the idea of the first showcase I want to show is we want to exploring using of photoacoustic imaging to visualize those neurovascular bundle in an intraoperative manner in a surgical scene to help telling where the treatment should not be happening. So that's our main problem to talk about first. But again, this is the picture of Da Vinci surgical robot. The one of the main challenge that we need to overcome first is the size of the instrument. Okay, so in order to bring photoacoustic into this scenario, those conventional ultrasound probe or conventional fiber optic is too bulky, right? So ultrasound probe can be maybe smaller, but the typical fiber used for photoacoustic imaging is more like a forward-facing fiber bundle, which is quite bulky, and in order to deliver sufficient light source, you need to have its own size. And those fiber or coupling device will definitely not fit into this space here, right? So the first thing that we want to think about is how we can miniaturize that. And we're starting from using ultrasound device used in a clinical scene already, right? So this is the laparoscopic ultrasound probe, which will fit into around 10 to 15-ish tracker size that they can let the port like tool goes through. And that's the hard constraint. So we only have access to this space, and we need to package both light source and sound receiver all together to do photoacoustic imaging. So we saw like, how about we have a fiber in a way that can deliver the light without requiring big fiber bundle. So our approach is to process the fiber, and instead of let the fiber to go forward, but let the light going through in the middle. So in this case, we are using so-called diffusion fiber. So the light will going to the sideway, so that we'll have creating sufficient illumination widths and also the depth coverage to realize pretty much similar capability what those conventional fiber bundle can do, but with only one fiber or two or three fiber. But it's sideways, so we can significantly miniaturize the size. So we do those quantitative analysis to checking that if the illumination is homogeneous, is going sufficient energy. Then we're also checking the image quality that we do see those fiber in ultrasound view, have multiple of them, and we can actually see quite well with photoacoustic imaging, right? Then the last thing that before bringing to the Da Vinci surgical robot system, we want to check if this is sufficient to give us those neurovascular bundles. So we want to see the nerve and also want to see the blood vessel. And that's where we are targeting lipid and also hemoglobin contrast. And with the algorithm, we actually can see like blood is coming from the muscle, so everywhere. So we have a lot of hemoglobin signal coming from the rat thigh, and also the lipid. We can see those bundle light up in green and showing that those are area that we want to tell surgeon to avoid. Okay, so we know this instrument will work. The next thing that we want to do is to bring it integrated into Da Vinci surgical robot system. So we basically put this laparoscopic probe mounted on the robotic arm, and that will go inside of the surgical scene. And we can integrate that with the camera vision. So we can not only scan the vessel, but also we can see that from the camera view, because that's the only camera that surgeon can see. So we want to feed the information in an effective way, right? So what this is showing is we are preparing a chicken breast, and in this chicken breast, we embedded blood vessel, which containing blood. So from the top, we cannot see what's inside, and that's what surgeons' view are typically when they are facing the patient. But those imaging can take a cross-section shot, right? So those cross-sectional shot can be overlaid on top of the camera view from the Da Vinci console. Then we can basically in real time showing those overlay. Then what ultimately they want to know is how deep indeed those vessels are from the surface. So we can map the depths of the vessel from the camera view so that they can tell how the tool should be coordinated and so on. So this is actually very exciting direction. We are currently working with Medtronics and think about how we can make this procedure more stable and also tolerate with some motion, because organ will move over time. But with very, I would say, like recent computer vision advancement, there are a lot of algorithms that we can compensate that. So we were trying to, translating this concept hopefully in a more clinical setting. All right. So we speak about where not to treat. The second thing I wanted to more focusing on is where to treat, right? So we remove the skin layer and get the organ exposed. The next question is when they are treating the tumor or cancer or those area, we want to make sure that we are treating in a right spot or right area. So in that sense, we are targeting prostate cancer as one example clinical cases. And for the prostate cancer, the main challenge is it's it typically have not so much problem in terms of survival rate, but survival rate will drop significantly when the patient get to, cancer start to get metastasized. So it's very like a silent disease, but once get aggressive, they need to treat right away. So the critical clinical need is indeed to finding when is the timing that the prostate cancer will become aggressive. So for that problem, we tackle through a molecular approach. Particularly, we are targeting a molecular target so-called PSMA. It stands for a prostate-specific membrane antigen. So this protein is expressed with the prostate, but overexpressed with aggressive type of prostate cancer. And a study have shown that this PSMA can effectively differentiate in the Gleason score 3 and 4. So basically, when clinicians do histopathology of the prostate cancer cell, they want to know the boundary between Gleason score 3 and 4, because if they go to 4 or more, those patients probably need to better go with radical treatment or radical, prostatectomy. But 3 is considered more like a mild. So it's very, like a boundary that to differentiate the treatment strategy. And this PSMA actually will play the perfect role in that sense because it has very high sensitivity of differentiating between those 3 and 4 grade. So what we want to try to show here is we know that PSMA is a good target, molecular target, and we want to show that photoacoustic can visualize those agents because this PSMA is currently already well evaluated in a PET or SPECT, those nuclear medicine approach, and already undergo human subject testing. But as we also know that the limitation of nuclear medicine is radiation. So if we want to have more like a bedside treatment or diagnosis, they want to have more or less, radioactive approach in that sense. And photoacoustic in that sense, is not introducing radiation. We saw that can be another alternative to compatible with those treatment strategy. So what we did is we are preparing two tumor on a mice model, and we basically put the 2 tumor here, and these 2 tumor each representing prostate cancer. One do have PSMA expression, and one do not have PSMA expression, and that will basically tell one of them, like for example, this one is more aggressive form, but the left one is less aggressive one. And if you're looking at the ultrasound, like this time, the aggressive one grow more, but we cannot telling much from the image by itself because the tumor itself does not have anatomical or variation in terms of appearance. But when we're looking at the photoacoustic, before and after injecting the contrast agent, we actually can selectively see that the signal is only coming from the aggressive prostate cancer. So this is the first step that we were trying to show that we indeed can use photoacoustic for this molecular targeted imaging to tell where the distribution of PSMA is. In other words, we can see the prostate cancer. Then the second phase that now similar to the previous example, we first want to show the principle. The second, we want to show the translational instrumentation and how to adapt into the patient scenario, right? So in order to adapting those imaging capability into a hospital setting, the one testing that we want to show is how this type of photoacoustic imaging can be compatible with the MRI-guided prostate intervention, which is kind of like a gold standard right now for topical guided biopsy procedure, right? So that's our goal now. So the second goal of this study is we want to make sure we have an imaging system that can be cross-validated with MRI. In other words, we want to have a system that can go inside the MRI, can take MRI image, ultrasound image, and photoacoustic imaging at the same time. So what we did is we built a MRI-compatible robotic scanner where this is the ultrasound and photoacoustic head, which can provide like two-dimensional cross-sectional scan, but also have a 2-degree of freedom rotation to get the volume like this, and also give a fan beam scan to capture sufficient field of view. And this is the robotic system. Everything is MRI compatible, so can go inside the MRI bore, to move those scanner to get the volume data. So let me show you how it works. So this is the MRI scanner that we have, and we put the probe and as an imaging target. In this case, we prepare 3 tubing phantom. Okay, in this tubing phantom, we containing 2 tubes containing contrast agent and 1 tube containing water. So basically, this is the MRI view. We can see 3 tubes clearly, and with the ultrasound view, we can see 3 tubes again, right? But with MRI and ultrasound, we can see the structure, but it's not necessarily informative in terms of which one containing contrast agent, which one is more indicated with the tumor that we're interested in. But with the photoacoustic imaging, now we can selectively see that only 2 tubes light up, because that only two tubes containing contrast agent, so that we can differentiate between even tissue one that have more molecular expression and some is not. Then what we are doing right now is we want to further translating the idea and testing with a mice model. In this case, we are scanning a mice. First, we want to building the tau where we can see the volume with MRI, then also with the ultrasound overlay with a photoacoustic. In this case, we haven't injected contrast agent, so we are more seeing about the blood distribution of the tau. And then more recent study that we are trying to image the tumor on mice where before and after injecting contrast agent, we can see that contrast agent can well distributed to the organ. Then we can see we can use this platform for imaging tumor. So these are efforts that we're still ongoing and trying to creating a way that using ultrasound photoacoustic, working with MRI for finding where the tumor is, where to treat. Then the last part about the imaging side is where to stop the treatment, right? So I know Dr. Sean also working on the AFib and arrhythmia treatment, but the main interest here is when there are treatment like not only cardiac but also for liver, there are certain treatment that are using heat to burn in the tissue, right? So, but the problem is those procedures are currently happening in a blind way, meaning that it's very tiny space, so they can treat it, but they have no way to see if the tissue is being treated or not. And the treatment for arrhythmia is basically burning the muscle fibers to prevent abnormal electrical pathway to go through. So they really want to make sure that there's no gap between those treated lesions and ensuring that the entire area is being covered. So they want to have some sort of feedback to ensuring that area coverage is sufficient. So we saw okay, if we can have photoacoustic imaging to see the lesion formation in terms of the size and also the depth, then we probably can use this information to tell when to stop the procedure to prevent excessive treatment and also to prevent the recurrence. And to be clear, we're not the first group to introduce using photoacoustic for those tissue imaging. There are groups in the past exploring finding the spectral characteristic in photoacoustic before and after tissue is being treated. Just like we see when tissue is being I would say treated, or like we cook the meat, we can see the color of the meat will change, right? So there's a change in optical characteristics. And there's also some group that can see that in an interventional fashion, so suggesting that photoacoustic can be a potential solution for those problems. So what we did first to tackle this problem is we want to define a clinical index that clinician would like to use. In particular, what they want to get from those imaging is they don't care much about the signal itself, but they very want to know the boundary of the lesion. So particularly they want to know the size, the width and depth of the lesion, and they are not want to missing that lesion is covering, for example, too much to creating severe complication or making sure the width is covering sufficient to not having any gap. And we first showing that, okay, the width do have good overlap, have a high correlation, and the width also have good correlation with histopathology. So we first showing that photoacoustic indeed is effective. Another interesting finding actually we got from this study is we found that this type of photoacoustic reading or necrotic depths have a correlation with acoustic impedance change. Sorry, not acoustic, like impedance change with electrical pathway, meaning that this is what actually doctor ultimately want to know, want to make sure that tissue is indeed being blocked. And we can find that when we are ablating certain area, we can ensure that impedance is achieving higher than certain resistance. And we can use this as a benchmark, for example, to decide when the treatment should really stop. Because the cardiac wall, for example, have certain sickness limit, right? So they cannot like keep burning and creating a halt. They don't want to do that. So if we can use those metrics to tell them how to control the treatment strategy, then we can hopefully solve a lot of problems they have. The last result I want to show here is a demonstration in vivo. So this is happening in a live pig, and we are burning the tissue at the surface of the heart, and we place an imaging sensor from the top. And this is ultrasound image. You can see that the muscle, the cardiac tissue is moving up and down. It was a live pig, and if we overlay the photoacoustic signal, we can see that the blue is showing the non-ablated, but the red and yellow one is showing the ablated tissue. So in a cross-section, we can identify where the treatment is happening. It's very challenging experiment because tissue is moving so dynamically, but we are getting that we are stepping the first step to show that we are approaching to this problem. Apparently relevant to the previous one example, we want to also have a translational capability, right? We don't want to just stop at the imaging capability. So we're building the instrument that incorporating the fiber optic technology that I mentioned earlier through side firing. So we actually can have photoacoustic capability with ICE probe, and which do provide good imaging depths and field of view. And we show that it do capture this area coverage as we show in a bigger probe. So that to suggesting that we do have a capability to translating from the concept into the translational aim. All right, so these are topic more for about imaging part, right? So we're talking about we can use ultrasound photoacoustic to see like where should not treat and where should be treating and where to stop the treatment. Then the second half I want to cover about how robotics can help those imaging. And actually, I have two quick case study or example to this end. Basically, both are talking about how robotic can do something that human cannot do. And the first case is for kidney transplantation. Okay, so kidney transplantation, what is important is to know the organ health before being transplanted. In fact, like a lot of people, we all kind of have impression that we are in short of the kidney or organ to be transplanted. But the real problem is not just we don't have a donor who want to donate. We do have a kidney, but it just takes too much time to assessing its health, it's in the right condition at the right timing. Because it's getting too old, then we lose the timing, then we not be able to use that kidney for transplantation. So it's that timely assessment is very important for this procedure. And currently they are doing histopathology, for example, which takes time. OCT is a promising alternative that I think you're probably already familiar with OCT, but it's sitting somewhere here in terms of the imaging depths as well as the resolution. It do capture around less than 10 micron spatial resolution, which is perfect for this kidney health assessment because the key anatomy that we are interested in is the tubular structure of the kidney that is typically around 8 micron, and so which is fit into the resolution that OCT is able to capture. So our goal here is to build a system that using OCT to do those organ assessment, but the main challenge here is this is a handheld device, for example. It's going to be very, very painful for surgeon to scan all of them, making sure it cover entire coverage of the kidney. So we thought like, okay, why don't we do this with a robot, right? That's a good reason that we're now introducing a robot to do this procedure automatically. So this robot, for example, can read organ and recognize the shape and recognize orientation and automatically calculating the right path, then we can build a map that collecting all the information. Hopefully, we can build a whole kidney map. So this is an example of the video that we have. Robot arm is moving and it's adjusting. I mean, we definitely don't want the robot to touch the organ. So it automatically sensing the depths, but also don't want to be too far away because field of view or OCT is also limited. So we want to make sure that always there is maintained. This is the surface of the organ, and by scanning different slices, we are little by little collecting and gathering information, and ultimately we want to use all the information to build an entire kidney map. And just those are some of the tissue that we are getting, and that's where we want to quantify. So let's say we want going through the entire kidney, then this is what we get. Okay, with one scanner view is probably around this size, but we are kind of like able to stitch entire land. It's like really like a continent, but we are imaging kidney continent with the robotics combined with imaging that human alone cannot do. So regarding the clinical significance, so what we want to find is those tubular structure visible in OCT and which capture around comparable size where we can have in a histopathology, and we want to build this in an entire kidney so that making sure there's more kidney can be used for transplantation. Some more recent advancement that we want to leveraging the intelligence of robot more. So I showed earlier that things can be streamlined with a robot automatically, but if we actually adapting into clinical setting, doctor also want to provide some input that not necessarily entire kidney is what they want to know, but they want to have some manual operation as well. So in this case, we have a robotic arm, which can be controlled by the joysticks, but this kind of robotic system will never touch the kidney because of this safety barrier. So basically, the robot will have this intelligence to getting close enough, but once the surgeon is trying to touch it, it will get the resistance. And so that we can always get the surrounding, and so that we can do like we call this as a shared autonomy. So we have autonomy with a robot, but also we share this autonomy with a human. So this is like more, I would say, cooperative fashion that we want to envision how human working better with robotic system in the future. The last example I want to show very quickly is also in ultrasound part, because in this case, I wanted to show you one more intelligence the robot can have. So the previous one is more like they have a kidney, they can see the shape, they can get the entire scan, right? But ultrasound now they need to read the images and interpret those clinical context, right? So in this case, we have one more AI agent to do those intelligent part. So the first step, for example, we can have an AI agent to tell the robot where the scanning should be happening. For example, this camera can capture the patient body. Then we can have an AI network to recognize where's the head and where's the body. For example, here you can see there's a mannequin, but this mannequin has a labeling here, right? So the labeling here is actually not what we put the number, that's what AI put the number. We train with another model, and they will automatically label this. So patient, if they move, they will automatically follow the position, so that making sure the robot can scan all the area effectively. Then the second one is most of the time the question when we introduce robotic system is about the safety, right? So in this case, our safety is to making sure that robot can never ever damage the patient. If patient move, patient twist the body. For example, this those sensor can capture the surface and always trying to follow the curvature of the body so that will not be able to damage the patient. And this is another example that we are currently testing with 20 to 30 human subjects, both male and female, where we want to show this robotic ultrasound scan can capture those anatomical landmark in a therapeutic and automatic fashion. The last part I want to show here is more like intelligent part where we want to have the robot to read those images and recognize where is the anatomical landmark is located. In this case, we're talking about lung disease cases. So there are some shadow from the bone. There's also some lung skin surface. Those are appearance in ultrasound images. And those agents will allow the robot to label those target and can do those so-called template matching to compare with where the idealistic imaging view should be versus where the current view is. So there's some control algorithm for that. But as a demonstration here, we put the probe, and even if we move away the probe, if we're trying to push it away, the robot will always trying to come back. It's like a balancing robot that when I always trying to take a balance. If it's trying to go out of view, we still want to have a robot to recover. So this is some of the human subject testing to show that this is showing the image similarity, looking at how image collected by the robot can be similar to what human can be acquired. So over time, it's getting back to its idealistic goal. And lastly, I want to show that we can acquire higher than 90% similarity compared to robotically acquired data with human acquired data. So it's very rushed, but the last part I wanted to show is the potential that introducing robot may help many of your research. Some part in terms of helping expanding the field of view, some in a sense to be more controllable or standard way. So one of the goals that I want to show in this application for ultrasound is with different patient body size and different organ, as long as we have a good reference, we can define the robot to be trained. We can realize those control and standardized scanning. To wrap up my talk, I basically wanted to introduce the concept that how imaging can be merged with robotics and how imaging can help robotics can help imaging, right? So first part I'm talking about how advanced imaging can see those tissue characteristics that without those imaging we couldn't see. So that hopefully can open up new treatment strategy or diagnose strategy for the future. Then the second of all, I wanted to mention about how robotics can help those imaging so that now we can achieve the imaging that imaging alone cannot do, or we can do more imaging in an intelligent way so that with less user dependency in a more standard way. Before closing, I want to appreciate all the funding source and collaborator and the lab people to make those research happening. And I also want to thanks again for Dr. Shang for this opportunity. And we would like to thank you all for attending the session. Looking forward to answer any question or let me know if any comments. Thank you.
So for the robotic ultrasound, the body scanning for like transthoracic ultrasound, how do you take the ultrasound images specifically over like rib regions and use that to inform like position and scanning?
Yeah, so maybe this is good schematic. So this is I would say like the final step. The first step is to find where is the chest area that diagnosis should be happening, and they can land to the location. And there's a fine adjustment based on our sensor in the previous slide. Here we get here, then the question is how to avoid those rib cage and how we can positioning. So what basically we train is if there is a visibility of the rib, if there is visibility of non-rib, we want the AI to recognize them. So we train two agents. One is to detecting the rib, especially like rib shadow. There's a shadow be constructed after the rib. So once we see those shadow, we can get the warning that these are something we don't want to let those artifacts to cover entire image. And also there are we call it a pleural line. It's a surface of the lung that we want to maximize that. So the agent currently is to try to maximize this pro line, and also making sure that there is a space in between rib shadow so that we have a window opening. And this is happening in 2D and 3D space. So in 2D cross-section, it will make sense just looking at this, but there's also orientation can happening. So the algorithm is actually considering both velocity component in a linear space and also angular space, meaning that it's trying to find this in a 3D configuration. I think that's what we do for that.
Yeah.
Yes.
And for the acoustic detection of blood vessels, it relies on hemoglobin, correct?
Yes.
Does it also detect flow? And if there's like a bleed in the field of view, it could kind of cover the ability to see the blood vessels. So does it also recognize flow of
Currently no, because we are more currently, let's say we're capturing hemoglobin, meaning that we are capturing the instance at that exactly time point, right? For example, we are shooting the light. That particular timestamp is where we can get as an image. But there are algorithms, for example, if we can get the sequence of those images, then we may be able to reconstruct the flow. But the major difficulty to do that for photoacoustics is the speed of the laser. Because of those big laser is typically slow. It's 20 Hertz that we use right now, meaning that the flow is running faster. So it's not as easy as ultrasound, for example, but there are some algorithms using, for example, like spectrum analysis or frequency analysis, try to recover this flow. But currently, we're not doing that yet. Yes.
I have limited knowledge of photoacoustic, and this might be a very stupid question, but I understand for detecting ultrasound waves, you need in between the detector and the sample, it needs to be like a gel, a medium. So for a surgical situation like the prostate that you brought up, do you just use gel as well, or do you don't need that because of the water inside of it?
Right, I think gel will be the most common. Yeah, so for the prostate case, that's how, for example, there's already a clinical practice called transrectal ultrasound-based biopsy, and ultrasound do face the same problem that you mentioned, the acoustic coupling, basically. Basically, there are two approaches. One is simply put tons of gel. Another is putting some sort of balloon with the gel filled and help using those balloons to push the tissue a bit more so that to help creating the boundary being coupled. And currently, the one result we're trying with large animal, and we're actually trying both, putting the balloon that with a probe coupled with the gel. And that gel is very well controlled, so it's very straightforward to go through that, and that is helping pushing the organ so that making sure there's always interface in the middle. Yeah.
Just a quick follow-up question is, do you clean it after? Because normal ultrasound was getting you wipe out the gel, but for inside the body, do you wash it away or?
We probably need to wipe it away, yes.
Oh, Dr. Zhao had
Go ahead, Dr. Zhang.
Okay, question regarding the robotic arm. Is it from commercial source or built in your lab? What's the approximate cost?
Right, that's a good question. So we are in a very fortunate era where robotic arm price dropped significantly since 10 years ago. And the arm that we are using in particular called Franca Amica Panda, that's a German company, and we can get it less than 40K, for example. And I think there's other universal robot that I also used before that is also probably similar price range. But being said that, if we really want to bring to the patient side, then we need to have a medical grade robotic arm. Then the most common standard one is from the KUKA. They have a medical grade robotic arm. That will be, I would say, triple or a little bit more cost than that. So there's a trade-off. But depending on how much, I would say, like a sterilization need and how much, those robots will interact with the patient, that will decide what the cost range would like. But I would say, yeah, less than like 50K people can really enjoy high level, like high-end robotic arm type of research. Like, by the way, the precision, like the difference between KUKA and those arm is not accuracy. I think the accuracy of this robot is already like a 0.05 millimeter, so it's 50 micron, so it's very, very precise. It's more like if the system will meet a medical grade standard or not. For research, we're good with that.
I see. Another question, the distance between the OCT probe and the skin is very, need to control quite precisely.
Yes.
Do you use sensor on the robotic arm or your own sensor to control the distance?
Very, very good question. We do use both. We use a sensor on the robot. We also use the image itself. So we're using OCT image, making sure that because there's only very tiny sweet spot to make sure the probe is not too away or too close. So we're initially using the large like optical sensor to get rough location. And when getting closer and start landing, they will see the structure in the images. And now we switch to imaging control mode, that using imaging to control the height so that we can have a consistent and always get the image. Because that's actually is a great that you asked this question, because that's we need to implement to make this procedure possible.
I see. Thank you.
Okay, yeah.
Okay. So I have a question regarding the lung ultrasound scan in human subjects. I assume the robot lets them breathe normally by adjusting the force. But I wonder, how do you make sure that the robot field of view is not changing while still allowing the movement of the normal breathing?
Right. We do allow the breathing, and we do allow the field of view can shift over time, but always the algorithm is running in the background to make adjustment. So they're breathing, but always the angle is trying to make a correction. So, you can think about that. Let's say you place the probe, then I move, then it's not like we find the location, it's done. It's a continuous process, yes. So there's several like a safety layer that need to run in the background, but for example, for example, this type of pipeline image acquisition and recognition part is running in the background, and also those sensor is also in the background. So they're always trying to minimize the error and try to adjustment.
It's just like a big picture question. So, well, first of all, I really enjoyed your talk. I really like the practical challenges that you were addressing, and really neat how you're doing this. So I'm just curious, you covered a lot of different topics, a lot of different organs, and what part excites you the most? What do you think is maybe you're closest to having something where it's going to be impactful?
Yeah, that's an excellent question. So the motto of our lab is, where there is a need, we'll work for that. We're trying not to work based on our interest and do something they're not interested in, right? So everything here is all, for example, brought from a clinician, or I would say some direction. Let's say prostate is one. I think we have already pushing very close to translation phase and want to pushing through. In photoacoustic, another is a cardiac. I think that two organ are what we want to do. For robotic imaging side, I think we're more open to that still. OCT for kidney is definitely, we see the need, and we are running clinical trial at Georgetown University. We're testing with a human live kidney, and ultimately, hopefully that can be a product. But I think for those general robotic things, we are actually exploring the need, and hopefully we can find that.
Thank you.
Okay. Any other questions? No, I do have one. So you showed that photo signal actually is proportional to the electric impedance.
Right.
So I wonder if you can explain what is the underlying mechanism for that. We know photoacoustic is sensitive to different absorption. Basically, you have color change. But why the impedance change related to photoacoustic?
Right. Yeah, I think that is more relationship between, let's say they are, 5 mm layer, right? Then if I just burning 1 mm, then there's still a lot of tissue they can let electrical signal to go through. But if I reach into, for example, 3 mm, that's where where it make it difficult to electrical signal to go through. So what we are trying to compare is how deep the imaging depths or like lesion depths they formulate is creating how solid that resistance is being formulated. We are thinking as a mechanism to have a great matching in correlation with the electrical impedance.
So that linearity is not the intensity of photoacoustic signal to the impedance. It is like the thickness.
Correct. Yes, that's not the intensity, but the area coverage.
Oh, that makes sense. That's great. How do you measure the impedance there?
Yeah, we put the electrode to the tissue to measure the impedance.
Oh. Okay, any other questions? No, thank you all.
Thank you.
Yeah.
Thank you so much. Yeah.
Yes, it's a great topic. Great.